example. So suppose you have an inclined plane, and its height is h, and you've got a sphere. And suppose that this sphere has mass m, radius r. And then so it's a bowling ball, but it's not the bowling balls that we use. I mean, this is more like a piece of cheese, a uniform cheese, which has somehow been sculpted into the shape of a bowling ball. It is uniform mass throughout. I mean, if you actually crack open a bowling ball, what do you find? It's got like a hard exterior shell, right? But it's not got uniform mass. I mean, it's mostly spherically symmetric because you don't want a lumpy bowling ball, right? That would, I don't know, maybe you do. Maybe it adds chaos to the, I don't know. But I would assume you want a uniform bowling ball, right? Which doesn't mean that it's got uniform mass. I mean, it is uniform shells of mass, right? But this sphere, though, I'm imagining is completely uniform mass, solid sphere. And it's rolling down the hill without slipping. It rolls down this hill without slipping over to this point here, and it's got some final velocity vf. And my question then is, if this rolls without slipping down to there, and no energy is lost to friction, all right, how fast is the ball rolling? See, that's the question. So in order to solve this problem, I need to share some some information with you, which is that the moment of inertia, and we'll talk more about different moments of inertia. Did she leave? Oh, okay. Good. So we'll talk more about different moments of inertia. To solve one of the problems on the quizzes I'll give you guys, you'll need to know more. But for the moment, this problem, it can be calculated with, well, you won't be surprised to tell me, you won't be surprised to hear me say with calculus, the moment of inertia can be calculated to be 2/5 mr squared. So the moment of inertia for a sphere is 2/5 mr squared. And the way we solve this problem is with conservation of energy. The idea is simply this. And let's suppose, to keep it simple, that the ball is at rest right before we let it go to roll down the hill without slipping, all right? So it's at rest to start with, and we just conserve energy. So energy at the top is equal to energy at the end. And the question is, what kind of energies are involved? Well, at the start, what kind of energy do we have? We simply have m g h, right? We have the gravitational potential energy to start with. But how about at the end? What kind of energy do we have at the end? What's that? I mean, we have kinetic energy, right? So, but what kind of kinetic energy we have? Well, I was trying to illustrate with my silly marker throw earlier that kinetic energy comes in two flavors. It comes in translational kinetic energy, but it also comes in rotational kinetic energy. So to describe the energy in this marker when I throw it, part of it's the translational kinetic energy, but there's also the rotational kinetic energy. And they're both conserved in the absence of torque or an external force. So the energy in the end is kinetic energy translational plus kinetic energy rotational. Now that's the new one. Right, that's the story we have not told before today. Great, so what are those? So big M GH is 1/2 big M V squared plus 1/2 I omega squared. because that's the kinetic energy of rotation for something with a moment of inertia I rotating with angular velocity omega. Now I said this in words, I haven't written it yet, but rolling without slipping. What's that mean in terms of, what does that say about the connection between V and omega? And here's something that I slipped. There's a couple things I haven't written here. And one of those things would be that, theta is equal to, well, I would say S is equal to R theta, right? But there's another one, which is that the tangential velocity, or speed, if you will, is equal to R omega. So now this is the final velocity. This is the final angular velocity, right? What am I interested in? Yeah, which do I want to keep, the omega or the V? I want V, right? I need to get rid of the omega. How do I do that? Yeah, substitute. Omega F is equal to VF divided by R. Now, if you just think about that for a second, it makes so much sense. Like if I want to find the number of radians per second, I take the number of meters per second, and I divide by the radius, right? Because every time you go through a radius worth of arc length, that means you've subtended a radian of angle. So this formula makes perfect sense, that we should take the translational or tangential velocity and divide by the radius. That gives us angular velocity. So put that in here. What we got? We've got 1/2 m VF squared plus 1/2. And now I told you that I was 2/5. Now that's for us, that's magical. You need calculus 3 to derive that probably. And omega F is VF, but that's okay. We have a table, so we don't need to derive it. We can just look it up, as we will. So that's VF over R quantity squared. And see what happens? Check that out. So the R squareds cancel. See that? The R squareds cancel out. And we've got what? 1/2 m VF squared plus, it looks like 1/5 m VF squared. So let's see here. As a, if I were to take the ratio of kinetic to translational kinetic energy, what's the ratio of translational to rotational? It's 1/2 over 1/5, right? So there's 2.5 times as much translational, I think, as rotational in this situation. Anyway, put it together. What you got? You got, what's 1/2 plus 1/5? It's 5/10 plus 2/10, 7/10, yeah? MVF squared. And so there we go. VF squared is equal to 10 GH over 7. So VF is the square root of 10 GH over 7. Now, if, we could have, of course, I could give you the mass is 13 kilograms and the radius is 3 centimeters and so forth and so on. We could put numbers in here, but I didn't want to distract from the physics this time. The bigger picture is that we have to account for rotational kinetic energy when rotation is something we can understand for the problem. Any questions about this one? I hope not. I have given you a similar but much more complicated problem for the quiz. So you probably have figured out I'm not going to make you do this quiz in class today. I mean, I want to go home. So, you too. So here's the deal, guys. I will let you work on this. So I want you guys to work on these in groups of 3. So you pick your 3. You can work in group of 2 if you'd rather. Maybe you only have one friend. I don't know. Or maybe you have 2 friends, but only one of them is smart. Could happen. And I actually have quizzes 5 and 6 here. There are 4 problems. I'd like to collect them next Tuesday. All right? The first problem is almost verbatim my first example from today with different numbers. I give you 3 masses. I tell you kind of where they are. I say the center of mass is at the origin. I say find the location of the 4th. The second problem is I give you a torque. I give you a moment of inertia. I ask you to find angular velocity, angular acceleration, angular position, and revolutions made in 10 seconds. That's quiz 5. Quiz 6, I'm sorry, I didn't put points on. How many points should these be worth? 20 each? 50? 100 each?
Yeah, the exam.
You guys are funny. Quiz 6, problem 1, I give you a force, I give you a point. I say calculate the torque about the origin. That's the example I just erased up here with hopefully different numbers. I did have a 7 in the z here though. Ooh, what was my x component for the r? Was it 2? I don't know. My numbers in this quiz are kind of close to your And then this one I'm proud of. Problem 2 on quiz 6, I have a wheel with spokes in it. And it's rotating down, it's rolling down an inclined plane, find the final velocity. So this problem is analogous to what I just was working through here. However, the wrinkle is you're going to have to figure out what the moment of inertia is for a wheel with spokes. So I'm going to try to do some examples Thursday which show you how to find moments of inertia for more complicated things. We can kind of it's like Legos, right? You can build more interesting sets from smaller sets. It's the same thing with moments of inertia. It's additive in a certain way. We'll see. Anyway, make sure, tell you what, rather than handing these out, let me put them at the back. You can get one as you're leaving, and we'll call it a day. I will also, for those of you who are